Okay, hello everyone. My name is Sulaf Alfares. I'm a third-year medical student, and today I will be giving you a lecture on the topic of Pentose Phosphate Pathway. Inshallah, this topic isn't very hard. Once we go over every slide, you're gonna understand it very well. Before we start, I just wanted to ask you guys if you're attending this as a revision or as a first study, just so that I understand the kind of questions I can ask you guys. If you could just write in the chat. Okay, first study. Okay, great. Inshallah, then I'll simplify it as much as possible. Please try to make this as interactive as possible. If there's anything you don't understand, feel free to unmute and ask me, or just write in the chat. I don't think I'm gonna be able to look at the chat. So if I get anything, Atman, if you can just tell me that I got like a comment and if you can read it to me. Okay, with that being said, let's get right into it. Okay. So these are our objectives. Inshallah, we're going to cover all of them. Before we get into the deep stuff, let's just have an overview of everything. So what is the pentose phosphate pathway? Basically, it's just another way that the body can utilize glucose. You studied other metabolic pathways in which glucose is very important, and this is just another one of them. And it consists of a group of reactions in which glucose 6-phosphate is degraded and is transmitted into other reactions. And if you studied the previous cycles, then you know that glucose 6-phosphate is a part of glycolysis. So it's important to note that it's a common intermediate with glycolysis. And this is an alternative pathway that we can get into once we have a lot of glucose 6-phosphate. Okay. This pathway is also known as the HMP shunt, and you're going to find out why in a minute. Okay. The purpose of this pathway is to create two things. The first one being NADPH, and the second one is ribose 5-phosphate. Please remember those two things, very important. And we're going to discuss the benefit of each one of them in a bit. This pathway occurs in the cytosol, and it has two phases, and we're going to discuss them all in detail. And the last important thing to keep in mind is that in this pathway, we're not going to gain or lose any ATP molecules, okay? Okay, now I have a couple of important definitions. I need you to make sure you guys understand because I used to confuse them a lot when I was in first year. So can someone tell me what is oxidation? Just write it in the chat. Do you know what it is? Okay, I'll just say it then. Oxidation is basically the loss of electrons, while on the other hand, reduction is the gain of an electron. And how to remember this, because I used to get confused by reduction, but it's a gain. Basically, when you gain an electron, the atomic charge is going to decrease. You're reducing the atomic charge, okay? So remember, when you reduce something, when you subtract something, you're making it more negative. And electrons are more negative. So basically, this is what happens in reduction, okay? And finally, shunt, it just basically means to move someone, or in this case, something from one place to another. And we're gonna see what we mean by that. Okay, back to those two main products of this pathway. We said the first one is NADPH. NADPH stands for nicotinamide adenine dinucleotide phosphate. That's a pretty lengthy name. You don't need to know all of that. Just remember NADPH. And remember that it's an electron donor, okay? It donates its electron, meaning it's gonna get oxidized, right? So keep that in mind. And it's important for three things. One, it's gonna help us synthesize fatty acids, cholesterol, and steroid hormones. Another way this could be mentioned in questions or like when you read about this, it's gonna participate in anabolic reactions. As we know, anabolism is the creation of molecules from smaller things. And it's also going to participate in reductive pathways, okay? So all of these three things mean the same thing, just remember them. And where is NADPH important? In three main organs, the liver, the adrenal cortex, and the lactating mammary glands, okay? The second important point is that it's going to help us in the reduction of glutathione. And glutathione is an antioxidant, and we're going to talk about it in more detail in a minute. And finally, it has bactericidal activity, which means it's going to help us kill bacteria. And NADPH is created in the first phase of the pentose phosphate pathway, which is the oxidative phase. The second thing, which is important, is the ribose 5-phosphate, which is a precursor for PRPP, which is the precursor of nucleotides, which make up our DNA and RNA, okay? And this is going to be created in the second phase or the reductive phase. Okay, let's talk about NADPH again. In the liver, we already said it, it's gonna participate in the biosynthesis of many different things. Now, what's important is the neutrophil, because in the neutrophil, it has very important bactericidal activity. We said that the word bactericidal just means that it's going to help kill bacteria. And basically what happens is that when we have pathogens like in our blood, they're just roaming around, they're gonna get recognized by phagocytes, such as neutrophils and macrophages. So the neutrophil is gonna come and it's gonna notice a pathogen and it's gonna be like, no, we need to get rid of this. So what the neutrophil is going to do is engulf that pathogen, okay? Once that pathogen is inside the neutrophil is going to kill it using something called a reactive oxygen species. Did you guys hear about reactive oxygen species before? I don't think you guys did yet, because it's the lecture, I believe, after this one or 2 lectures after this one. So I'm just gonna tell you about reactive oxygen species very briefly. Basically, they're molecules which have capability to be which have at least one oxygen atom and unpaired electrons, and they have the capability to alter the DNA, or they can also alter the structure of the cell wall, okay? And this is actually how they induce the killing of the pathogens. So what happens is basically it starts with an oxygen molecule that gets converted into a superoxide anion, okay? This happens through the action of an enzyme called NADPH oxidase. So it's going to utilize NADPH. And as the name says, oxidase, meaning it's going to take one electron from the oxygen and it's going to give it to NADP positive for it to become a superoxide anion, okay? And then we have a long pathway of reactions where MOL molecules are going to get created. And finally, we're going to get bleach, which is going to kill the bacteria, okay? Okay, after that, we have glutathione. We already mentioned that glutathione is an antioxidant. From what I said, reactive oxygen species are good, right? They help us kill pathogens. However, if we have a lot of them, they're going to turn bad, because they're not only going to attack the bacteria, but they're also going to attack our own cells, and they're going to cause DNA damage and a lot of other things, okay? Which is why if we have a lot of reactive oxygen species, we need to neutralize them using glutathione, which, as we mentioned already, is an antioxidant. And just for now, remember that it's very important in red blood cells. We're going to talk about that in more detail later, okay? So how does this work? On the left, you can see the what we already talked about, which is called the respiratory burst, in which we create reactive oxygen species to kill bacteria. On the right here, we have the function of glutathione. I'm going to show you just this other graph. Okay, when we have this molecule, we want to neutralize it, okay? This is the hydrogen peroxide molecule, and we want to make it into 2 H2O molecules. This happens through the enzyme glutathione peroxidase, which takes glutathione, okay, and it oxidases it and creates glutathione disulfide. So we're going to have 2 things now, glutathione disulfide, and we're going to have H2O. Now, for this glutathione to be able to function again, we need to bring it back to the reduced phase, right? This happens using NADPH. NADPH is going to donate its electron, and it's going to give it back to the glutathione so that we can keep this cycle going. This happened through the action of the enzyme glutathione reductase. Do you guys get this point? Okay, so basically this is how glutathione functions to help protect us from reactive oxygen species, okay? Okay, after we discussed the function of NADPH and ribose 5-phosphate, let's get into the actual cycle, okay? So when we look at this, it looks a bit scary and complicated, but we're gonna break it down, okay? On the left, we can see glycolysis, and we can see that we have glucose 6-phosphate in the beginning of glycolysis. After that, we're going to shunt it into the pentose phosphate pathway, which is why this is called the HMP shunt, or the hexose monophosphate shunt, okay? So the first thing that's going to enter the pentose phosphate pathway is glucose 6-phosphate. And let's look at the reactions happening in the first phase of pentose phosphate pathway, which is the oxidative phase, which is also called the irreversible phase. So this is all you need to remember. All those three reactions are irreversible. First, we have glucose 6-phosphate, and we're going to turn it into 6-phosphogluconolactone by the enzyme glucose 6-phosphate dehydrogenase, okay? It's a bit of a mouthful. We just need to repeat it a couple of times to keep remembering it. But I want you guys to remember that this is the most important step of the entire pathway. And as you can see, the enzyme, I put it in a different color here because this is the rate limiting step. Does anyone remember what the rate limiting step is? Can someone tell me? Come on, I need someone to write in the chat or just unmute and tell me what the rate limiting step is. Come on, anyone? Okay. A rate limiting step is basically the slowest step in a metabolic pathway, and it basically determines the overall rate of the pathway, okay? So in our case, the pentose phosphate pathway, glucose 6-phosphate dehydrogenase is going to facilitate the it's going to facilitate the rate limiting step, and it's also going to produce the first NADPH of this pathway, okay? We said NADPH is one of the most important products of this pathway. So just remember that. If you forget everything about this lecture and you could only remember one enzyme, I want you to remember glucose 6-phosphate dehydrogenase. And for short, we call it G6PD, okay? I want you to also notice that this enzyme ends in dehydrogenase. Whenever we say dehydrogenase, I just want you to remember that there is going to be a transfer of electrons, okay? And this is the first step. Now we're going to move on to the next step. 6-phosphogluconolactone into 6-phosphogluconate. When we read this 6-phosphogluconolactone, it's such a long name and we don't like it. So this enzyme, which ends in A's, and if you've seen from previous cycles, anything that ends in A's is probably going to cut something, okay? And in this case, we're just gonna make this a bit shorter and cuter. So 6-phosphogluconolactone is going to turn into 6-phosphogluconate, okay? And this reaction is going to utilize H2O and is going to release a hydrogen atom. This isn't very important, but just keep that in mind. And finally, we're going to go to the last step of the oxidative phase. 6-phosphogluconate is going to be turned into ribulose 5-phosphate by the enzyme 6-phosphogluconate dehydrogenase, okay? We can notice the word dehydrogenase again, meaning there's probably going to be a transfer of electrons, meaning this step is also going to release NADPH, okay? So two steps are going to give us NADPH, the first step and the third step. So keep that in mind. And the rate limiting step is utilized by which enzyme? Can someone write in the chat? Come on, this is easy. It's right in front of you. Yes, G6PD, absolutely. Glucose 6-phosphate dehydrogenase, or G6PD, is going to facilitate the rate limiting step of this process, okay? And it's also going to release NADPH. Okay, this is basically the same thing and just a different picture. Do you want me to go over it again or should we move on? I'll just wait for one person to tell me. Are you good or should I repeat? Clear. Okay, perfect. Okay, moving on. We have feedback inhibition. Does anyone know what feedback inhibition means? Basically, it means if we have too much of one product, it's going to go back to the beginning of the cycle or wherever, and it's going to stop it. It's going to be like, okay, that's enough. We got enough of this product. Please stop making more of it. Okay. In this case, the thing that's going to cause feedback inhibition is NADPH. Whenever we have too much of it, it's going to go back to the rate limiting step, which is facilitated by G6PD, and it's going to inhibit it. Likewise, when we have low levels of NADPH, it's going to stimulate this pathway, okay? And one other thing you should keep in mind, insulin. When we have insulin, it's going to stimulate G6PD to work, and also when we have NADP positive, okay? So just remember, NADPH, if we have too much of it, it's going to inhibit G6PD, okay? Okay. We actually made it to this point a lot quicker than I thought. This is just a checkpoint. I want to make sure if you guys understood everything so far or if you need me to repeat anything. Is everything good? Okay, great. Then to make sure you guys are paying attention, I have a question for you. Just read the question and tell me which do you think is the answer. Yes, perfect, E. So the main function of the pentose phosphate pathway is to supply us with two things. Pentose sugars, which is just another word for 5-ribose phosphate, as well as NADPH. Good job. Okay, let's move on to the second part, which looks very scary, right? However, don't worry, because you actually don't need to know all of this. There's only one important reaction in the second phase of the pentose phosphate pathway, and we're going to talk about it in a minute. However, for now, I just want you to remember that the second phase is important for creating ribose 5-phosphate, which, do you remember what ribose 5-phosphate is a precursor of? What is it going to help us create? One very important thing. Do you guys remember? Okay, no problem. Ribose 5-phosphate is basically a precursor of nucleotides, which are going to help us build DNA and RNA. Okay, so just keep that in mind. Remember this. Okay, also, I want you to notice how everything in this slide is double-sided. Like we have double-sided arrows, which is because everything in this phase is reversible. Basically, we're just gonna shuffle all of these reactions based on what we need. So whatever the body needs, we can go back in this pathway, we can go forwards to create whatever the body needs, okay? Now let's talk about that one important reaction in this phase. Okay, so the last thing we get from the oxidative stage is ribulose 5-phosphate. And then this ribulose 5-phosphate has two fates. It's either going to be turned into xylulose or ribose. And this is going to happen by two enzymes, ephemerase and isomerase. I added them myself. I don't think you need to know them. They weren't mentioned in your lecture. This is just for your information. Anyways, so ribulose is going to give us two things, xylulose and ribose. Now, transketolase is going to come. This enzyme does this thing where it takes two carbons from one thing and gives it to the other. In this case, transketolase is going to take two carbons from xylulose and it's going to give it to ribose. Also, just keep in mind that both of these things have 5 carbons in the beginning. So after transketolase works on them, we're going to get 2 products. And it's basically just shuffling carbons. This is the entirety of the reductive phase of the pentose phosphate pathway, okay? Anyway, so after shuffling those carbons, we're going to get 2 things. Cedoheptolase 7 phosphates and glyceraldehyde 3 phosphates, which, as we can see, one has 7 carbons and the other has 3 carbons. And I don't think you guys actually need to remember any of these like products. The most important thing to remember is transketolase and the fact that it's going to shuffle 2 carbons. And the most important thing about transketolase is that it requires a very important cofactor, which is thiamine, okay? Does anyone know what's the other name for thiamine? What vitamin is it? Do you know? Just write in the chat if you remember which vitamin. Okay, no, actually it's not 12. So thiamine is vitamin B12, and you're gonna have a separate lecture on each of the vitamins, but just keep this in mind. It might help you later on. Okay, so thiamine pyrophosphate, which is vitamin B1, is very important for the function of transketolase. If we don't have enough if we don't have enough thiamine, we're gonna get something called Wernicke-Korsakoff disease, okay? Before we get into that, I just wanted to ask, do you guys remember what other enzymes require thiamine? They're not from this pathway. I'm just testing your knowledge if you remember anything from previous lectures, and it's okay if you don't. But if you remember any of them, do write them down. I'll wait just a minute. Okay, I don't think any of you guys remember, and I don't blame you. They're kind of confusing. You need to go over them again. However, those are the enzymes, okay? We have 4 enzymes here that require thiamine as well as 4 other cofactors. Do you guys know the mnemonic that we have here? Dr. Hannah told you about it. The mnemonic is basically the lovely coenzymes for nerds. Do you remember the coenzymes? This isn't part of this lecture. I just wanted to refresh your memory and see if you know these from other lectures. So the lovely coenzymes for nerds, just for your knowledge, they're thiamine, lipoic acid, CoA, FAD, and NADPH. And all of these 4 enzymes require them, except transketolase, it only requires thiamine. Anyways, this was just a fun refresher about other lectures. Okay, moving on, let's talk about Wernicke-Korsakoff disease. We said it happens due to a thiamine deficiency. This is very important because when you get a question on this, not only from this lecture, it's going to be repeated on the alcohol lecture. You're going to take it again next year in your neuro block. Basically, what happens is that you're going to get a scenario about someone who's a heavy alcohol drinker, okay? And they're going to come to you presenting with mental confusion, vision problems. They're not going to know where they are. And all of these lead you to thiamine deficiency. The question is probably going to ask what enzyme, what deficiency does this person have, and what enzyme should we test for, okay? And just like we said, this is related to transketolase enzyme, okay? Okay, now moving on to the second important clinical correlation of this lecture, which is G6PD deficiency and hemolytic anemia. So you guys already took this in your foundation block, I believe, that hematology was a part of it. As we said, G6PD deficiency is going to cause deficiency in NADPH, okay? Because that first step is the rate limiting step, and it's going to give us the first NADPH molecule of the pathway, okay? In the beginning, I asked you guys to remember one group of cells that are important. Do you remember which ones they were? I didn't explain them, I just told you to remember them. Can you remind me what they were? Yes, excellent, red blood cells. Okay, So I didn't tell you guys this then, but basically, there is another organelle that can create NADPH. However, in red blood cells, we don't have that organelle, and we can only create NADPH through the pentose phosphate pathway. Can you guys guess, or do you know which other organelle forms NADPH? And just write it down if you can guess it. Okay, so the other organelle that forms NADPH is mitochondria, and red blood cells lack mitochondria. So they're not going to be able to create NADPH from anything other than the pentose phosphate pathway. Okay, that's one reason why G6PD deficiency mostly affects the red blood cells. The other reason is because red blood cells have a lot of oxygen, which means they're more prone to develop reactive oxygen species, because from the name, we need oxygen to create reactive oxygen species, okay? And if we don't have NADPH to detoxify the free radicals, it's going to lead to hemolysis. Remember, reactive oxygen species are going to cause a cell wall disruption, and they're going to cause DNA damage, okay? And this is basically going to lead to hemolysis of the red blood cells. Okay. Dr. Hannah said that this is the most important slide in the lecture, so I just added it as it is. It's basically everything we just said, but let's just make sure we know everything again. If we have a mutation or a deficiency in G6PD, it's going to lead to a decreased enzyme activity, which means less NADPH, which means less reduced glutathione, more reactive oxygen species, more cell wall damage, and more hemolysis. Okay? Does this make sense? Is everything clear? Just tell me if everything clear or if you need me to repeat anything up to this point. Yes. Okay, perfect. Okay. By the way, we're almost done, and you guys are doing very well. Let's just talk more about G6PD deficiency. Basically, it's an X-linked recessive pattern, and the scenario you're going to get is probably a male who is from either African or Asian descent, and it's also actually very common in the Middle East. My cousin actually has this, and it's usually asymptomatic unless you do one of three things, okay? Three things are going to lead to oxidative stress and will lead to hemolytic crisis. So what are those three things? One is infections. Two is the consumption of fava beans, which are basically fuel. And lastly, some drugs will create oxidative stress, such as anti-malarial drugs, okay? Which is funny, because people with G6PD deficiency are actually protected against malaria. So just remember this, they're already protected against malaria, so you should not give them anti-malarial drugs, or it's gonna give them a hemolytic crisis, okay? And finally, you probably know this from your hematology block, but G6PD deficiency is going to lead to jaundice, it's gonna cause anemia, and we're gonna see Heinz bodies and white cells, and I'm gonna show you those right now. Okay, so this is probably my favorite slide, and this is how I memorized it. It might be stupid, but on the left, you can see full or fava beans. And I don't know if you know this brand, Heinz beans, okay, but this is how I remember it. Basically, when you eat Heinz beans, you can see them inside the red blood cells. You see those Heinz bodies. Heinz bodies basically look like beans, okay? Or sort of, at least, you have to get creative when you're a med student. Anyways, so you have those Heinz beans, or Heinz bodies, I mean, okay? And they look like beans. So when a macrophage is passing by, they're gonna see the beans or the Heinz bodies, okay? And the macrophage is very hungry. They work hard all day long. So when they see the beans, they're gonna take a bite out of them, which is going to give us the bite cell, okay? So this is just one way to remember it. Okay, now this is a table basically summarizing the entire lecture. And by the way, you guys, we're done. This is basically it. We're just gonna go through a few questions. But my tip for you guys is I want you to make a table like this on every single MOL lecture you get, especially the cycles, okay? These are the main things about every lecture: the location, the product, the phases, which one is the rate limiting step, what cofactors are needed, and what is the clinical significance. Do you guys want me to go over the summary before we do the questions, or do you want to go straight to the questions? Summary. Okay, let's just go over it one more time. Okay, the pentose phosphate pathway happens in the cytosol of all cells, almost, okay? The two main products of the pentose phosphate pathway are one, NADPH, which is important for three things. Biosynthesis of many different things, okay? And it's going to be a part of the respiratory burst, which is basically the bactericidal activity, which kills the bacteria. And finally, it's going to reduce glutathione, which is an antioxidant that is going to kill, which is going to neutralize reactive oxygen species, okay? The second important product is ribose 5-phosphate. Ribose 5-phosphate is an important precursor of nucleotides. Nucleotides are the building blocks of pyrimidines and things like that, which are going to create DNA and RNA, okay? Next, we have two phases in the pentose phosphate pathway. The first one is the oxidative phase, which consists of only 3 steps, and it's irreversible. And the most important thing is that in it is the G6PD, okay? And it's going to give us NADPH. The second phase is the reductive phase, or the non-oxidative phase, which is entirely reversible. And this phase is going to give us the ribose 5-phosphate, okay? Now, as we just mentioned, the rate limiting step is catalyzed by glucose 6-phosphate dehydrogenase, or G6PD, okay? The most important cofactor is thiamine, or vitamin B1, and it's important for the function of the transketolase enzyme, which works by moving 2 carbon atoms, okay, between different intermediates. And finally, the clinical significance. We have 2 important things. First one is G6PD deficiency, which is going to present more in males of African or Asian descent, and it's usually asymptomatic unless you have one of the 3 triggers: ingestion of fava beans, infections, or anti-malarial drugs, okay? And we can see this in the blood smear as Heinz bodies and white cells. The second most important clinical significance is Wernicke-Korsakoff. Okay, Wernicke-Korsakoff happens due to thiamine deficiency, which means that the transketolase enzyme is not going to be able to function very properly. And you should know that the clinical presentation of this is in alcoholics who present with mental confusion and vision issues, okay? Okay, this is it. Okay, now we're gonna go to the questions, and I want you guys to please unmute to answer them. If you don't want to, it's fine, but I urge you to unmute. Like, I want one of you to read each question and try to answer it, okay? And inshallah, they're easy and you guys can do them, and we're gonna explain them all in detail. Okay, first we have a scenario, not an MCQ. A patient has G6PD deficiency, but is still able to synthesize nucleotides. What compensatory pathway explains this phenomenon? I want someone to unmute and tell me how this happens, okay? Or what do you think? Or write it in the chat if you don't want to unmute. Does anyone want to try answer, or should I answer? Come on, guys, you can do it. Okay, I'll answer this one, but for the next ones, the MCQs, you have to answer them, okay? Okay, so patient has G6PD deficiency, but can still produce nucleotides. How? Okay, let's look at the cycle again. The first part of the cycle is irreversible, and we need glucose 6-phosphate dehydrogenase to be able to do this, right? However, the second part of the cycle is one, reversible, and second, has common intermediates with glycolysis. So fructose 6-phosphate, we can get this from other pathways such as glycolysis, and we're gonna make it enter into this pathway, and we're gonna get ribose 5-phosphate through this interaction, which in turn is going to give us nucleotide synthesis and DNA and all of that, okay? So this is how, if we have G6PD deficiency, we can still make ribose 5-phosphates and as a result, nucleotide synthesis, okay? Is it clear? Okay, the chat just disappeared, 1 second. Okay, I don't know why I can't see the chat. So I'm gonna need you guys to unmute to answer, okay? Okay, someone unmute and read the question for me, please. I really don't know why I can't see the chat. So I'm really gonna need someone to please unmute. Or Athman, if you can tell me if anyone answered in the chat, I'm gonna read the question. A chronic alcoholic presents to the emergency department with nystagmus, peripheral edema, pulmonary edema, ataxia, and mental confusion. The physician orders a test to determine if there is a vitamin deficiency. An enzyme used for such a test can be which of the following? Okay, just tell me, please, if anyone answered in the chat or if anyone wants. Yeah?
Someone said C.
Okay, C. Exactly, actually, absolutely right. Do you want to explain why? Or can you tell me the diagnosis? So just tell me if someone wrote down the diagnosis.
B1 deficiency, and someone else wrote something wrinkle thing, something like that.
Okay, yes. Okay. So the diagnosis is Wernicke-Korsakoff disease, and it happens due to thiamine deficiency, and it is C. You guys are absolutely right. And as we said, the tips in the question would be alcoholic and confusion. And they asked about a vitamin deficiency. So khalas, you're gonna know they're asking about B1 deficiency or thiamine. Okay. Next question. You're seeing a male patient of African American descent whose grandparents live in a chloroquine-resistant malaria belt in Africa. He wants to visit his grandparents and you want to give him primaquine as a malaria prophylaxis. But before you do so, you should test the patient for which of the following non-symptomatic enzymatic deficiencies. Again, you can unmute to answer and explain, or just write it down and please tell me if someone wrote it down.
D and anti-malarials will trigger.
Yes, perfect. Okay, D, glucose 6-phosphate dehydrogenase. This patient has a G6PD deficiency. Again, it's a young male from an African American descent. So we should know that this is the demographic predisposition of this condition. And before we give him a malarial drug, we should test him for G6PD deficiency. Because if he has it and we give him an anti-malarial drug, it's going to lead to a hemolytic crisis. Okay, is everything clear so far? Okay, the last question. A 25-year-old African-American male in good health had read about fava beans in Silence of the Lambs. For dinner one night, the man had liver with fava beans and a nice Chianti. I don't know what that is, honestly. About 8 hours after eating the beans, the man was tired and weak. Blood work showed hemolytic anemia. The patient most likely had a defect in regenerating which of the following? So we discussed this in the beginning, so I hope you guys still remember.
C.
Perfect, yes. Okay, so the patient has G6PD deficiency and the red blood cells cannot convert oxidized glutathione to reduced glutathione. So we need reduced glutathione. Is this clear? Okay. This is the last question. Before I move on to the last thing I want to show you guys, do you have any questions? Is everything clear? Just write yes or no, or repeat anything.
Yeah, there are no questions.
Okay. Okay, finally, I just wanted to give you guys my tips for MOL 1 because honestly, I feel like a lot of people like to scare freshmen about MOL 1 more than MOL 2. But in my personal opinion, I feel like MOL 1 is easier and it's more fun to study. And one thing that really helps me for MOL 1 is the blurting method. At the time, I did not even know that there was a name for what I was doing. But basically, specifically for the cycles, after studying, I would take a piece of paper, I would turn off my laptop, and I would draw the entire cycle, okay? All the enzymes, all the steps, the cofactors, rate limiting steps, everything, okay? And don't open, even if you forgot a step, just move on to the next one. And at the end, open and just fill in the gaps. And I feel like this is going to help you remember so much, especially that you can visualize MOL1 cycles, okay? You can draw them and everything. So I would highly, highly recommend the blurting method. The second tip for you is just two YouTube channels that I really liked. In Arabic, specifically, the first one, Science Bites. They're usually short videos, like literally 10 minutes max, and he explains them like in a really fun and easy way. And if you want a channel in English, JJ Medicine is really good. And lastly, the last tip is the same as the table that I created. And I showed you guys in the beginning, actually at the end of the lecture. But if you create a table like that for every single MOL lecture, I feel like it's gonna help you get like 90% of the questions right. Okay. This is basically it. That's all I wanted to teach you guys today. Inshallah, you guys benefited. I hope I made everything as clear as possible. Please scan this code to give your feedback on the session so that we can improve in the future. And please go over this again. MOL, you can forget things, so just don't get discouraged if you don't remember them right away. If you have any questions, I left my number. Feel free to text me on WhatsApp, and inshallah, I'm gonna clear up anything. Like if you encounter any question you can't answer regarding this lecture, I'm very happy to help. And yeah, this is it. Does anyone have any questions or anything they want to say? Okay, if not, we're done. Thank you guys so much for attending.